Okay, so recall that in the previous video, we stopped with the following expression, and our goal was to show that the limit of this summation was actually equal to 0, proving that both the original integral and the new one are actually equal. So recall that ui was a shorthand for g of xi, and that delta ui was of course ui, the right-hand point, minus ui minus 1, the left-hand point of the ith interval, which of course if we write back in terms of g, ui is g of xi, and ui minus 1 is g of xi minus 1. And now we are going to focus on this term specifically. This is the key to our solution. Once we pin down how big, or perhaps I should say how small, this term is, we will be able to show that the limit of this expression indeed is equal to 0. So let's rewrite the second term of our summation. Now delta ui again is g of xi minus g of xi minus 1. Minus the second term. And now here we have a difference of g at two distinct values of x, so we can apply the mean value theorem. G of xi minus g of xi minus 1 will be equal to the derivative of g at some point between xi minus 1 and xi. Call this point, say, xi bar, times the change in x, xi minus xi minus 1. That is the length of the ith interval of the original partition along the x-axis. And again, this point is somewhere between xi minus 1 and xi. Now, because we chose the uniform partition of the original axis, of the original interval from a to b along the x-axis, we know that xi minus xi minus 1, being the length of the ith interval along the x-axis, of course, is delta x, where delta x was b minus a over n. We took a uniform partition of the original interval from a to b, so we can rewrite this by delta x. And now delta x is a common multiple of both terms, so we can factor it. So we have now g prime at xi bar minus g prime at xi times delta x. And now we can repeat the argument of the mean value theorem of differentiation one more time. We had originally a difference of g values. Now we have a difference of g prime values. So again, we assume here that all the functions and their derivatives are also differentiable. So g prime is assumed to be differentiable. So the difference of g prime values will be, by the mean value theorem of differentiation, equal to the second derivative at some point between xi and xi bar, let's call this point xi double bar, times the change in x, so xi bar minus xi, times delta x, where again xi double bar is some point between xi and xi bar. Now since xi bar is less than xi, this means that we will have xi bar where am I? yes, this is the smaller point of these two, so this being in the middle, or somewhere in between, will be bigger than this point, lesser than xi. But as we'll see, it doesn't really matter. Now what we want again is not the exact expression for this, but an upper bound. How big, or perhaps how small can this be? Well, we make here an assumption that, or perhaps now is a good time to go back to the original expression. Yes, I will do this in those two steps into one step. So we now have rewritten the second term of our summation in this form, and I will now bring back in the f of ui. So this gives us, this implies that the ith term of our summation, f of ui, times this, which is this term right here, will equal, again, f of ui times, now not the original form of the expression, the second term, but the new form of the expression. And now we want to look at the size of this term. So we take the absolute value of the ith term of our summation. And this is where things get interesting. Recall that ui is g of xi. So we are taking here values of f at points inside of the interval from g of a to g of b. Right? So we have the initial interval from a to b along the x-axis. Then we have the new interval from g of a to g of b along now the u-axis. And if you're noticing here, we're taking now the second derivative at some point inside the interval from a to b, and we are taking f at some point inside the interval from g of a to g of b. And now here are our last two assumptions. We already had assumed that our functions were differentiable and their derivatives were continuous. So here we assume that f specifically, to highlight the two conditions we meet. You see at this point we've used the fact that g double prime existed, and we will also assume that g double prime is continuous on AB. That is our first assumption. Since we are evaluating the second derivative of g at some point between a and b, we assume g double prime is continuous on the interval from a to b. Then we are evaluating f at some point inside the interval from g of a to g of b, so we will assume that f is continuous on this second interval. And now we will quote the extreme value theorem. In the range that we are considering of x values and g values, both g double prime and f are continuous. Therefore, their product will also be continuous. Therefore, both functions will attain their maximum value in absolute value. So g double prime will attain a maximum value in absolute value inside of the interval from a to b, and f in absolute value will attain its maximum value on the interval from g of a to g of b. So the product will be at most a fixed constant as long as x is between a and b and u is between g of a and g of b. So this means that the product between f at any point times g double prime at any point will be absolutely bounded by a fixed constant, say m. So m is a fixed constant. And now let's pin down the size of this term, right? If we go back, both xi double bar and xi bar were in between xi minus 1 and xi. And so the length of this difference is at most the length of the full interval, which of course is delta x. So in absolute value, xi bar minus xi is at most delta x in absolute value. Now of course here we assume that a was less than b, so delta x equals delta x in absolute value. And now we are good to go. We have an upper bound. For any value ui and any value xi double bar, this product between f and g double prime in absolute value will be at most a fixed constant m. This in absolute value is at most delta x times delta x. Therefore we have delta x squared. Now we are ready to go back to the limit, but not quite yet. We will look at the absolute value of this summation. So what do we now have with our upper bounds? And we will also make use of the triangle inequality. We have the original, if I just show it back for 1 second, we have the original summation right here. Let me rewrite it. And we will take the absolute value of this expression. Now by the triangle inequality, the absolute value of a sum is at most the sum of the absolute value of the individual terms. But as we have just shown, if we go back, the absolute value of our individual terms is at most a fixed constant times delta x squared. So each term here is at most m times delta x squared, so we can bound the sum above by summing the larger terms, which is m times delta x squared. And now what's interesting is that this upper bound no longer depends on I. With respect to I, this is a constant, right? M is a constant, and delta x, being b minus a over n, no longer depends, or I shouldn't say no longer, never depended on I. So we can factor this out of our summation. So this will be equal to m delta x squared times the summation of 1. But this is not a trivial summation. If you sum 1 as I ranges from 1 to n, you are summing 1 n times, right? This is 1 plus 1 plus 1 dot 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 plus 1. And again, as I ranges from 1 to n, we are summing 1 n times. So of course the result equals n. Now this may be alarming because we said we wanted to show that this summation in the limit as n tends to infinity would actually go to 0. But now we have a multiple of n, and we are letting n tend to infinity. So this seems like a bit of a problem. But remember, delta x is a constant over n. Now we can replace. So m, delta x is b minus a over n. We squared the whole thing times n. So we will have m times b minus a squared. This is an absolute constant. Then times n over n squared, which of course simplifies to 1 over n. So what we now have is m times b minus a squared, an absolute constant over n. Now think of what this means. The absolute value of our summation is at most an absolute constant over n. Let's now rewrite this concisely. The initial term and its upper bound. So we have an absolute value. Our summation. Being at most this fixed constant over n, and obviously since we have here an absolute value of our expression, this is at least as big as 0. And now if we let n tend to infinity, we have a fixed constant over n, which of course goes to 0. As n tends to infinity. So the left-hand limit is always 0. The upper bound is approaching 0. So in the limit, our initial summation in absolute value has to converge to 0 by the squeeze theorem. That is the only option. As it is getting squeezed between 0 and 0, it must converge to 0 as well by the squeeze theorem. So this proves that if something in absolute value goes to 0, of course, it means that the expression itself must be approaching 0. So this implies that the limit of our initial expression without the absolute value is equal to 0. But if you recall where we left off in our original video, this expression is exactly equal to the difference between both definite integrals. This was equal to the new integral from g of a to g of b of f of u du minus the original integral from a to b of f of g of x g prime of x dx. And since this is equal to 0, right, the difference is 0, then both integrals have to be equal. Just send this term over to this side, and we can now write our resounding conclusion that indeed the differential gave us the right answer. The new integral is indeed equal to the original integral. And so what is the big takeaway here, right? Fundamentally, all we did in the original slick argument why these would have to be equal was that the exact length of the new intervals of the partition in the new integral could be not found exactly, but approximated by the differential, which is the linear approximation, and that this approximation is good enough so that in the limit, the new integral equals the original one. And again, we know that as the initial intervals of the original partition tend to 0 in size, the smaller delta x is, the closer du, the differential, is to delta u, the exact length of the new intervals in the second case. And so as delta x goes to 0, therefore as n goes to infinity, this approximation gets better and better and better, and it is sufficiently good so that in the limit we do not need to find the exact length of the new intervals of our second partition, but instead approximate them by the linear approximation given by the differential, and that this approximation again is good enough to return the exact answer. So hopefully this shows that when it comes to integrating and making a substitution, the notion of differential is legitimate. And again, all it says is the differential is the linear approximation of the exact change in the function, and so when it comes to the size of the intervals of the new partition, it is enough to estimate them by the linear approximation being the differential. And that's it.